Let us look at cases where non-integer coefficient equations are given to us. Now, up to now, we have mostly worked with equations whose coefficients were integer. What happens when they are not? So, we'll take them up one by one. The first case is fraction coefficients. We have 1 by 4x plus 2 by 3 is equal to 0. We can convert them to integer coefficients. So we take the LCM of the denominators and we combine these two terms. We get 3x plus 8 divided by 12 equal to 0, which is 3x plus 8 equal to 0. And now this we are very familiar with. How to solve? Let's look at a cubic. 1 by 2 x cube plus 3 by 4 x square minus 5x plus 7 equal to 0. Again, combining them, we get 2x cube plus 3x square minus 20x plus 28 divided by 4 equal to 0. And 4, if we take it to the other side, it disappears, leaving us with our familiar integer coefficients. So if some or all of the coefficients are fractions, we can multiply the equation by the least common multiple of the denominators to convert all the coefficients to integers. How about decimals as coefficients? 0.75x square plus 0.25x plus 0.3 bar is equal to 0. 0.3 bar is nothing but our recurring decimals. Now, how do we handle this? First, let's convert this into a fraction, 0.3 bar. So let t is equal to 0.3 bar. Multiply both sides by 10. So 10t is equal to 3.3 bar. Now subtracting, 10t minus t is equal to 3.3 bar minus 0.3 bar. We get 9t is equal to 3. So t is equal to 3 by 9, which is 1 by 3. So our equation becomes what? 0.75 we know is 3 by 4x square. Otherwise, you can just divide it by 100. And simplify to get 3 by 4. Similarly, 0.25 is 1 by 4. So 3 by 4x square plus 1 by 4x plus 1 by 3 equal to 0. And now we have got the fraction coefficients, which can be converted into integer coefficients. 9x square plus 3x plus 4 divided by 12 equal to 0. So 9x square plus 3x plus 4 equal to 0. Let's look at this. We have 0.6 x cube plus 1.25 x square minus 0.6 bar x plus 0.5 equal to 0. So again, we have to convert that recurring decimal into a fraction. So let t is equal to 0.6 bar multiplied by 10. So 10t equal to 6.6 bar. Subtracting, we get 10t minus t is equal to 6.6 bar minus 0.6 bar, which gives us 9t equal to 6, which gives us t is equal to 6 by 9, which is equal to 2 by 3. So our equation becomes 6 by 10 x cube plus 125 divided by 100 x square minus 2 by 3 x plus 1 by 2 equal to 0. Simplifying, we get 180 x cube plus 375 x square minus 200x plus 150 divided by 300 equal to 0, which gives us our familiar integer coefficients. But this can again be simplified further by dividing throughout by 5. 36x cube plus 75x square minus 40x plus 30 equal to 0. Now, terminating and recurring decimals can be converted to fractions, so we can then convert the coefficients to integers. Now, let's look at radical coefficients. Square root of 2x plus 1 equal to 0. So, root 2x equal to minus 1. x equal to minus 1 by root 2. And we don't want root 2 in the denominator. So we rationalize it to get minus root 2 by 2. Now we cannot convert root 2 to an integer coefficient. If we multiply by root 2, then the constant becomes root 2. Let's see what I mean by that. Multiplying throughout by root 2, we get root 2x times root 2 plus 1 times root 2 equal to 0. 2x plus root 2 equal to 0 and 2x equal to minus root 2 and x equal to minus root 2 by 2. So we can't really convert this into integer coefficients, but we can still solve it. Let's look at another one. Root 2x square plus 3x plus root 2 equal to 0. Now this is where the quadratic formula is very useful, since factoring the expression may involve some mental gymnastics. Formula works perfectly. X equal to minus 3 plus or minus square root of 9 minus 4 times root 2 divided by 2 times root 2. Simplifying it, we get x equal to minus 3 plus or minus square root of 9 minus 8 by 2 root 2. So x equal to minus 3 plus or minus 1 divided by 2 root 2. Simplifying it, we get x equal to root 2 times minus 3 plus or minus 1 divided by 4. And splitting it, we get x equal to root 2 times minus 4 by 4 and x equal to root 2 times minus 2 by 4. Simplifying those, we get x equal to minus root 2 and x equal to minus root 2 by. Let's look at this. Root 2 plus root 3 x square minus root 2 minus root 3 x minus 1 equal to 0. Again, we use the quadratic formula. So, x equal to, this is minus b by 2a plus or minus square root of b square minus 4ac divided by 2a. So, look at it carefully. Here minus I have taken it inside. So, minus root 2 plus root 3 square minus 4 times a times c. Simplifying it, we get this. Further simplification gives us this, and if we want, we can rationalize the denominator. Now the above ugly expression is a precise value for the roots of the given equation. So basically what I'm saying is, we have reached a stage where simplifying this is more of a arithmetic exercise rather than an algebraic. Now let's look at some special numbers as coefficients. So let's look at an example. Pi x plus 1 equal to 0. So pi x equal to minus 1 and x equal to minus 1 by pi. Another example, ex square plus pi x minus 1 equal to 0. Now remember, e and pi both are constants. So we apply the quadratic formula. X equal to minus b, that is minus pi, plus or minus square root of pi square plus 4e. This minus and the minus of the b square minus 4ac becomes plus. Natural log of 2x square plus 3x plus pi equal to 0. Again, quadratic formula, minus 3 plus or minus square root of 9 minus 4 times natural log of 2 times pi divided by 2 times natural log of 2. So as you can see, whatever be the coefficients, our algebra what we have learned still stands. Now let's look at non-real complex coefficients. So we have 4 plus 3ix plus 7 plus 8i is equal to 0. 4 plus 3ix is equal to minus 7 plus 8i. So x equal to minus 7 minus 8i divided by 4 plus 3i. Now let's rationalize the denominator by multiplying and dividing by the conjugate of the denominator. So x equal to minus 7 minus 8i divided by 4 plus 3i times 4 minus 3i divided by 4 minus 3i. Denominator is a plus b times a minus b. So 4 square minus 3 square I square. And the numerator becomes minus 28 plus 21i minus 32i plus 24i square. Simplifying it, because of this I square, this becomes minus. Because of this I square, this becomes plus. So we have x equal to minus 28 minus 11i minus 24 divided by 16 plus 9. So x equal to minus 52 minus 11i divided by 25. Let's look at another example. 2 plus 3i x square plus 3 plus 2i x plus 3 equal to 0. Now this is a quadratic. So we apply the quadratic formula. Minus 3 plus 2i plus or minus 3 plus 2i square b square minus 4 times a times c divided by 2 times a. Simplifying it, we get minus 3 plus 2i plus or minus square root of minus 19 minus 24i divided by 4 plus 6i. And again we can rationalize the denominator. Now let's look at a combination of all this. An ugly equation. We have pi minus natural log of 2x square plus e minus square root of 3i x plus root 5 by 2 equal to 0. Remember, ugliness is in the eyes of the beholder. For some it is beautiful because it is challenging. So in such cases, it is better to map the coefficients to the corresponding coefficients in the general form of the equation. So a is equal to pi minus log 2, b is equal to e minus root 3i, c is equal to root 5 by 2. And then we apply the quadratic formula. It is no longer an algebraic problem. It is a numerical problem. Simplifying this into a value for x or values of x because of this plus or minus. So to summarize, one thing we have to remember, we have looked at a lot of theorems, right, and results. So what happens when we use different types of coefficients? So let's summarize. So polynomial addition multiplication remains same, polynomial division remains the same, factor theorems remains the same, remainder theorem same, Vieta's formula same, fundamental theorem of algebra same. Complex conjugates occur in pairs. Now, when we have non-real complex coefficients, then this is not applicable. Descartes' rule of signs, again not applicable when it is non-real complex coefficients. And rational root test is applicable only in case of rational coefficients. In case of real coefficients where it is not rational, not generally. And here it is not applicable. So before you apply these theorems or results, you need to be careful about what type of coefficients you are encountering. So that was non-integer coefficient equations. That's it for now.